Okay, so good morning everyone. Let's get started. So in the previous lecture, we have asked three problems, as you can see here, and the problems they themselves are pretty easy, but the notion to address these problems are different, and that we have told that we will study today. So let us introduce one after another the detailed structure of probability, what we will deal with. Okay. So first of all, when we talk about probability, we always assume that, or in the classical notion, it is always assumed that there is a random experiment. So, and that experiment may be conducted by human or may be conducted by nature. The features that defines an experiment as a random experiment are this: that it must have more than one outcomes. If an experiment has only one outcome, it is not called as a random experiment. It must have at least two outcomes. And the outcomes of a particular trial, when you are doing that, or nature is doing that, is not known in advance. And lastly, that the experiment can be repeated countably many times in identical conditions. So the first one is okay, well acceptable that it has more than one outcome. There are many experiments which has more than one outcome. The outcome of particular trial is not known. That is also quite readily acceptable. But the last condition often may not be satisfied. So it is put as an assumption, all these three are assumption. If these three holds, then we can call an experiment as a random experiment. So if there is a question mark, then there is a question mark for the third point of this assumption. But anyway, uh, this is just a mathematical structure given for it, and whatever we will see maybe this course or maybe in some advanced courses, that in spite of little perturbation of the third assumption, still many good results hold. So for give an example, tossing a coin, rolling a die, arrangement or shuffling 52 cards, all these are very common examples of random experiment. Now another definition comes, which is known as the sample space. And the sample space is nothing but the collection of all possible outcomes of a random experiment. So that means if you toss a coin, you will get either head or tail. Okay. So head and tail, two element set. If you roll a die, you will get 6 numbers, 1, 2, 3, 4, 5, 6. And if you shuffle 52 cards, then you will get any of the 52 factorial permutations. So the set containing 52 factorial elements, that number is huge. You try and compute that what is the order. Do it and tell me. The first experiment has 2 outcomes, second experiment has 6 outcomes. The third one, calculate 52 factorial. I think all of you are in front of computer or mobile phone, so you can do it.
Sir, of the order of power 67.
So some constant, power 67. This is a huge number. And now suppose if I ask you or give you a deck of cards and ask you, give me a randomly shuffled deck of cards, what will you do?
I will give you the card as it is.
Please be louder.
I will give you the cards as it is. That's
Okay,
also random.
that's also random. In what sense that's also random? Suppose I have given you the 52 cards in a natural order, numbered 1 to 52. And now I am asking to give me a randomly shuffled deck of cards.
This natural arrangement is also included in that 52 factorial.
Yes, but I know that. So I can tell what is there and what is not there.
So then,
So we will shuffle it.
Okay, you will
the
shuffle
way you
it.
define randomness.
Say again, please.
It depends on the way you define randomness. How it like the natural
Okay.
how is the natural arrangement is different from other things.
Okay, so
The
now
out,
the yes, please. Yes.
uh, uh, the outcome of the particular trail is known beforehand if you don't shuffle and give it to you. So you have to shuffle beforehand so that it can be called as a random experiment. If at all we give it in a natural way, uh, if at all you shuffle and it comes out to be a natural arrangement, then it will come under random experiment. But if at all I just give it to you in the same way that you gave it to me, then it can't come under random experiment because the outcome is already known in advance. It will
Yeah.
violate the second point
Yeah.
under the definition.
Yeah. Yeah. So now here we can ask another question that when I ask this term in English that give me a shuffle deck of card or randomly shuffle deck of card, then what we exactly mean? We exactly mean that having any permutation as an outcome which have equal probability, which is 1 upon 52 factorial. So I will get a permutation, whatever may be, with probability 1 upon 52 factorial. So eventually doing that thing, what it requires? It requires that you write down all those 52 factorial permutations and you choose one of them with equal probability. Now, as you have seen that it is of order, I forget what it told, 67 or something. So, having that number with equal probability is a very difficult job. It's really a difficult job. Do you think that whatever computer you are using will be able to do it? One number randomly chosen which has equal probability that and the order is 10 to the power minus 67. That is really a daunting task. But you see that whatever may be, the many casinos, they are using a random shuffle deck of cards. They say it is randomly shuffled. And you can understand how randomly shuffled it could be. Well, we will come across to this thing once again if time permits. So any query regarding the definition and the definition of random experiment and sample space? I think it is pretty simple part at this stage. Okay, now let us go for the classical definition. Classical definition, first assume that the sample space is finite. Okay. So we usually define the sample space by either omega or S. And if the number of elements in omega is finite, and then the probability of a subset of omega is denoted by P of A, and it is measured as the cardinality of A, that means the number of elements in A, divided by the total number of elements in omega. So this is the classical definition of probability. I think in your 10+2 level you have done this thing, and this is how you can not only mathematically tell what is the probability, and this is how you can also compute or estimate or approximate the probability. So this is in that sense very useful. So first of all, the cardinality of omega is known as the number of all possible cases, and cardinality of A, whatever pre-specified, which is a subset of omega, that is known as the number of favorable cases. So number of favorable cases divided by the number of all possible cases, and that is just the probability of occurring. And okay, so we will define what is an event, but occurring an event A. Now you can go back to the problem that we have discussed yesterday, that A1 plus A2 plus AR equals to N, R less than N. Then computer is giving you a solution which contains the natural number and 0. So what is the probability that all AIs will be natural number? And that solution we have already seen yesterday, that if you consider only natural number solution, then this is the cardinality of A, and if you consider 0 with them, then this is the cardinality. So probability will be this quantity divided by this quantity. So that is the thing that we have already discussed yesterday. We are not going to details of. Now again, and also to answer the first question, the cardinality of black card is 26 out of 52. So total number of cards is 52. So 26 divided by 52, that is half here. Okay, now let us address this problem, that a random number chosen from the set of natural numbers, what is the probability that it will be an even number? So here the first problem comes, that the cardinality of omega, that is the sample space, is no longer finite. So we cannot use the classical definition. We need to modify that definition. Okay. So how to modify that one? So this is known as the frequency definition of probability. You need to consider a sequence of, and so omega is the sample space, and A is a pre-specified subset of omega. So A is contained in omega. Now we have to define two sequence of sets. One is, say, AN, which is gradually increasing to A, and another set, omega n, which is also gradually increasing to omega. So you can assume that it is like a pond. So let me just draw it. You can assume that it is something like a pond, and so this is omega, and you have dropped a stone in the middle, so it is the ring type of structure, maybe something like that, and they are gradually increasing, so they are omega n. So omega n, so omega 1 is contained in omega 2 is contained in omega 3, and they are gradually increasing, and they all are contained. Sometimes it is known as the Russian doll sets. So one big doll, inside that a similar doll, and inside that a similar doll, in that way. So this is the set of omega, and an is also a set, so which is inside this, and it is also gradually increasing, but it has a maybe a boundary which is not as large as omega, but this is A, and this blue sets are an. So A1 is contained in A2, is contained in A3, and so on, and AI is individually contained in omega I. Okay. So this is the structure that we want to see, and then we define the limiting probability. Now all of them are finite. Now we define the limiting probability. So as n goes to infinity, cardinality of an divided by the cardinality of omega n. Okay. So let us see. So P of A is defined as limit n goes to infinity, cardinality of an divided by cardinality of omega. So following this result, if we consider omega n, omega n equals to say 1, 2 up to small n, and an is maybe say 2, 4 up to even numbers, so n by 2 greatest integer. I hope all of you, anybody doesn't know this function, greatest integer value less than equals to the number. So now here you can see with this definition, limit n goes to infinity, box of n by 2 divided by n, and that limit goes to 0.5. As simple as that. So now you can extend even this result, that what is the probability the number is divisible by 3, it is 1 by 3, or divisible by 4 is 1 by 4, so on and so forth it will be going. And many other things you can argue in this. But the interesting application of this result is when you will do many experiment and studies with your probability or estimation specially, or more precisely, say for example, when you will do some testing problem, then you need to calculate the power of the test, or if you do some estimation problem, then you need to estimate the accuracy of your estimator. Then repeatedly same experiment is done under simulation and the estimation is done. So how close it is to the true value, or how many times something is accepted or rejected, this count is done, and that result goes to converge to a certain number, which is a probability. A similar kind of experiment we will do today, and we will be able to see that how this convergence matters. If it doesn't converge, then we will be nowhere. But this definition eventually helps us in computation and approximation of the probability. So this is the key result to approximation of probability. So this is the key result, and this is the result implemented either by for theory or for computation. For computation, this is this, I mean, the result by which you can do the computation. Okay. Now, let us move
Sir, here
to,
in the an,
yes,
shouldn't the last term be n or n minus 1?
which one?
In the set an.
Yes.
So the last term should be n or n minus 1.
Sir, it can be 2 star step n by 2. You can write that.
No, I am considering in the last term is n by 2, then box function, greatest integer value.
Yes, sir, but
So
it is
if
not.
it is,
We
ah,
can
Then
write
the cardinality will not be n by 2.
2 into box n by 2. We should write.
Yes, sir, 2 into box n by 2.
which one?
Yes, sir. The last term would be 2 into box of n by 2. Because,
Oh, okay. Yes,
yes, sir. And the number of elements would be box of n by 2.
yeah. Number of elements is box of n by 2. Yeah. Thank you. Yes. 2 times box of n. Yes, correct. Yeah, correct. Okay. So, I ask you to construct a counter example where this definition will fail. Okay. Now we are moving for another. Uh,
Excuse me, sir.
yes, please.
Sir, I had one doubt in the previous definition. No,
Yeah.
in the slides itself, means the printed slide. Sir, there it is written that countable set. I did not understand. Means how is omega countable?
Okay. So a set is said to be countable if it has a bijection with the set of natural numbers. So here the omega itself is the set of natural number. So it is countable. There is no problem with it.
Okay, sir.
So I will share this LaTeX file with you. Maybe after 1 or 2 days, I am doing some editing, and there you will get the preliminary chapter. That is what I am adding to it. This one. So the cardinal definition of countability and how all those stuff works. This thing I am adding now. So maybe after 1 or 2 days you will get this thing, and either you will get the necessary information from here, or from here you can search in internet and study that. Okay, I'm just incorporating this part. This is not usually taught in this course because it is supposed to be done in Math 1, Math 2 type of course. Okay, so now we are moving towards the axiomatic definition of probability. And for the axiomatic definition of probability, we need to develop 2 more concepts, or maybe one more concept, sigma algebra or sigma field. But before that, we have a definition of algebra. So algebra is a collection of subsets of omega. So in omega, you have some number of elements, and then in this A is a collection of the subsets of omega. Okay, and it satisfies few properties such that the collection will contain the whole set. That means omega will be in that collection, scripted set. If A is contained in omega, A is a subset of omega and A is contained in omega, then A complement must also be in script. That means it is closed under complementation. The collection is closed under complementation. And if A and B both are subset of omega and A and B both belong to the script A in the collection, then A union B also belongs to that collection. So that means it is closed under finite union. If these three things happens, then we call that collection script A as a algebra. But if we can extend that idea to a countable union of subsets, and if it is closed under the countable union, then it is called a sigma algebra. So precisely saying, script A is the collection of subsets of omega, which is called a sigma algebra, if omega belongs to script A, if script A is closed under complementation, and if script A is closed under countable union. So why the countable union is needed, we will just tell you. But before that, few examples of sigma algebra. So phi is the null set and omega itself. So you can cross check that omega belongs to script A, its complement phi belongs to script A, and the complement of phi is omega, that also belongs to script A. Then again, if you take their union, it also belongs to script A. Similarly, if A is a subset of omega, then phi omega A complement, that also consists of a sigma algebra. And the first example, this is the trivial sigma algebra, which is the null set and the whole set. And the last example, which is the power set. So 2 to the 2 power omega, that means the power set. Okay, it is not a it is not a number, it is a set. This is the standard notation in mathematics, that 2 power a set represents the power set. That is not 2 power the cardinality of omega. It is 2 power omega, that means the power set of omega. Omega may be finite, omega may be infinite, omega may be countable, omega may not be countable. Okay. So these are the examples of sigma algebra, very trivial examples that we have given here. But in general, what happens, that we might not be interested to all of the probabilities, probability of all kind of events. We might be interested of a few particular type of events, although we have not defined yet, so we will define. But all possible subsets of omega, we might not be interested to that. So the construction of sigma algebra plays a big role. Given the construction of sigma algebra, we define the probability. So let us first define the probability, and after that we will do the rest of it. So this is the axiomatic definition of probability.
Excuse me, sir.
Yes, please.
Sir, in the sigma field or sigma algebra, you mentioned that subset A is a subset of omega and A is a subset of algebra A. Sir, if it is a subset of omega, then it will obviously be subset of algebra A, right? In the definition 19.
No, suppose if you have a collection where phi, omega and A is there, but A complement is not there in that script, then it will not be an algebra. Do you get my point?
Yes, sir, but in the definition, at the beginning we mentioned that algebra, A is an algebra.
Huh? So A is an algebra if it satisfies all these three conditions.
Yes.
Whole set must be there. If A belongs to that collection, A complement must belong to that collection. If AB belongs to that collection, then A union B must be in that collection. But that is not always guaranteed. The collection will hold that thing or not, that is not always guaranteed. To make sure that thing, we require these two definitions to hold that, you extend it for countable union, and then you call it a sigma algebra, and then it is satisfied. Is it okay?
Okay.
This is just to make the thing working, because in your course you might not get such examples where all these things will be violating. But if you go for advanced probability theory or stochastic processes, martingale theory, then you will feel the requirement of all this theory. Otherwise, in most of the cases, you will not feel the necessity of this thing. So I am not going to much details of this. I will just tell you one with a very small example how it works and where the difficulty is, but I will not go for those kind of example where you will get stuck with an algebra, I will not get a sigma algebra, this kind of thing I will not do, because that is not a idea of this first course of probability. Okay. So if script A is a sigma algebra of the subset of a non-empty set, see, and here is something is changing, of a non-empty set omega, then the probability P is defined as a function from script A, that collection, to 0 to 1, such that the probability of whole set is 1, probability of A is greater than equals to 0 for any A belong to this collection script A or the sigma algebra script A. If AIs belongs to script A, implies their countable union, the probability of their countable union can be evaluated as the sum of the individual probability where AI and AJ are disjoint. So when the sets are disjoint, then you can compute the probability. So that is a big advantage. So now with an example, let us try to see that. Okay, so let us try to see. So first of all, this is the advantage in computation. Why? Because if AI intersection AJ is null set for all I not equals to j, that means they are disjoint sets, and then the probability of union over AI, I running from 1 to infinity, that thing can be computed as probability of AI individual I running from 1 to infinity. So this is the biggest advantage of this technique. So this is the third point. Second point, that probability is greater than equals to 0. That is a trivial thing, and for that A must belong to script A. Otherwise, we don't know it. So probability of A is greater than equals to 0. And A is a subset of omega, and A belongs to script. And the first assumption is probability of omega is 1. The whole set has the probability. But at the top of this, probability is a function which is mapping from script A to 0 to 1. Remember, this is not, domain of the function is the sigma algebra, not omega. It is not omega. Often students do this mistake. Probability is a function from sigma algebra 2021, not from omega 2021. So the input of this function is a set. Output is a number lying between 0 to 1. Okay. So the input is a set. Input or argument of probability function is a set. Don't forget that. And where the set is in the collection of sigma algebra. Set is not in omega. Omega itself is a set. And whatever is inside omega, they are the elements. They are not the set. If you have to write them as a set, then you need to construct the algebra or the sigma algebra, and you need to consider the element of the sigma algebra as an input or the argument of the probability function, and the output will be 0 to 1. So any doubt, any query here? Notice one more thing, that we have initially talked about random experiment. Then we have talked about with random experiment we will get sample space. And then we have talked about we will get probability. But the definition that you have seen now, it starts from here itself. So they don't tell about the story behind. Whatever is happening and how you are getting this set, nobody bothers. You are given a non-empty set phi, omega, and from there the entire story begins. But in classical definition or the frequency definition, we start with the random experiment and then all that stuff. But in axiomatic definition, nobody bothers from where you get this set. This must be a non-empty set, and from there you have to have the sigma algebra, and this sigma algebra will be mapped to 0 to 1. So that is the probability. So this is a fundamental thing, and here nothing is specified about omega. Omega can be countable, omega can be uncountable, omega can be finite, omega can be infinite. It doesn't matter. As long as you have sigma algebra known to you and the probability assigned to it, you know everything. So here, let me, any query?
Sir, I have a doubt on the second point
Yes.
that you have mentioned in the axiomatic definition. Sir, you have mentioned PA is greater or equal to 0.
Yes.
Sir, isn't it obvious that it is?
So what?
So why we need to explicitly mention it?
No, the thing is, when I am mapping from 0 to, because look, they must not contain any negative number or any other number. So that is the main reason to say. So you have already mentioned that it is 0 to 1, and probability of, no, I don't find any harm to mentioning it, because
Sir, I
no.
mean to say that we could also get things without mentioning it, right?
if you say that so can you derive 2 from 3?
Sir, can you repeat please?
Can you derive 2 from 3?
2 from 3. No, sir.
Yes. Second statement from the third statement.
Achha, okay. Sir, but I mean to say that second statement is pretty obvious. I mean, for every by probability we means it is between 0 to 1.
Yeah, that is true. That is true. But for any set of, well, the main reason is this. Okay, I will come back to your question. Probability is between 0 to 1, that is true. I will give you one example, then you will get this point. So now just let us move on a little bit. That what is the now if I ask this question, what is the probability that a randomly chosen number from 0 to 1 is a rational number? And second question, it is less than 0.4. So first tell me the answer of the second question. You choose a random number between 0 to 1 and it what is the probability that it will be less than 0.4?
0.4.
0.4.
0.4. Okay. So how do you get this thing? Correct answer is correct.
Sir, consider a square of dimension 1 cross 1. So
Why? Your sample space is only 0 to 1. Why do you consider a sample space from the 1 cross 1 into 1 cross 1?
no, sir, I'm just trying to visualize it in a different way.
Yeah.
So just suppose we have taken a square of size 1 plus 1. So we are interested in finding the area of those things which are less than 0.4. I mean, it is our favorable case, favorable outcome. So the area less than 0.4 upon the total area, that is 1.
So you are saying in this way that so you are considering a square, so 0 cross 1 and 0 cross 1, then how will you get that area?
Sir, now our favorable case is something that lies in the area from 0 to 0.4. I mean, it is a rectangle of size 1 cross 0.4.
Okay.
Yes, sir. Yes, sir.
So what is the problem with this? If you have 0 to 1 and here is 0.4, and if you just instead of area, if you measure this length divided by the total length.
Yes, sir. That is also.
So the length of 0 to 0.4 divided by length of 0 to 1. So length of this set divided by the length of this set. Is it okay? Or any query here?
Sir? Sir?
Yes.
So does this mean probability of picking 0.4 from a set 0 to 1 is 0?
Yes.
Does
Correct.
it mean it is impossible?
Yes. It is not impossible, but it has probability 0. Probability 0 doesn't mean it is an impossible thing. You can have any set probability assigned to 0. And that is the main reason I have written this thing, or it is usually written that probability A is greater than equals to 0. Just to emphasize this thing, that even though the set is in the sigma field, it can have probability 0 also. So whoever is asking this question, have you got your answer? That
Yes.
is the reason. Okay. So
Sir?
yes.
Sir, if probability of A is greater equal to 0, and if we have mentioned it, then I mean, why do we mention it? Is there anything whose probability is less than 0?
No, there is nothing probability is less than 0, but it can be 0. It is not greater than 0 always. That is the major concern.
Okay, yes, sir, yes.
Okay.
I understood.
It can be 0. Okay. So it changed from context to context. Even people say that the event is occurring with non-zero probability. That doesn't mean that it will go to negative. It means with a positive probability. You will, if you follow the lectures of different contexts, specifically the probabilistic lectures or probability classes, then you often will listen this term that this event will occur with non-zero probability. So that means it will occur with positive probability. That is the thing. But in other context in mathematics, say for we say it is a non-zero number. That means it can be positive, it can be negative. It changes with the context. Now here you have identified the thing that the length of a point is, I am not going by what it is called. Okay, so let us do. So length of a point is 0, and as a consequence, now you can tell me what is this answer? What is the answer of this?
0.
So 0.
0. Why?
So there are only countably many rational numbers in 0 to 1.
Yes. So each of them with probability 0, countably many adding 0 is 0. So that is the main point. Okay. Now this is
the definition for the second, like each
Yeah,
of
please.
the point choosing from 0 to 0.4 is 0, and if we find a summation, then it will also be 0. We
Which one?
cannot.
Which one? Please say again.
The second question in example 22.
No, here, well, the set of rational real numbers are not countable. You cannot take the sum. The set of rational numbers Q is countable. but set of real numbers are not countable. You cannot take the sum, that doesn't hold.
Sir, how are rational numbers countable?
Which one?
Sir, how are rational numbers countable?
Rational numbers are countable. You can have a bijection from the rational numbers to the real numbers, or maybe r cross rational number to the natural numbers, or you can make it bijection to rational number to, or injection to rational number to n crossing. N cross n is also countable. Okay. So,
Sir, let's say 0.1. So that is a rational number.
yes.
So we can keep on going like this: 0.1, then 0.11, then 0.111. So all of them are rational. So how can it be countable? We can keep on going.
So you can map this thing with a bijection to the set of natural numbers. They are countable.
Sir, natural numbers are also not countable.
What?
Sir, I mean natural numbers.
No, ask one by one, please. Hello? One by one, please.
Sir, rational numbers are something which is written in the form P by Q, right? So, sir, there can be infinitely many rational numbers.
It doesn't matter. There are infinitely many natural numbers.
So then, how can it be countable? I mean, what is the real definition of countability?
The real definition of countability is this, that if there is a bijection between the set and the set of natural numbers, then it is countable. And you can have a bijection from the set of Q to the set of N or N cross N, which are also countable. So just to give you this kind of technical difficulties, I am asking these two questions. These kind of questions you will not face in this course as in exam, but as a first introduction, you must know this thing, because we cannot skip this part. Okay, you don't worry too much about this. Yes?
Sir, in the second question, how does the ratio of the length give us the probability according to the axiomatic definition?
Okay, so we will come to it, because for the time being, let us consider this is the definition. You have raised a very nice question, and we will try to tell you that if this may not be the probability, if it is not so here we define the probability in this way. It can be done in other way also. It can be done in other way also. Here I have yes, please.
Sir,
yes.
We can find sir. It is possible to find the probability of rational number in between the range of.
I didn't get your question. I didn't get your question. Hello?
Sir, it is possible to find probability of. Hello, sir. Am I audible, sir?
No, sir. No, you are not audible.
Hello, sir. Sir, I read in chat.
No, I can't hear you, man. Okay, so you read little bit about the set theoretic thing, and hopefully it will be clear to you. But it requires lots of rigor. So the thing is that what I am saying here, the axiomatic definition and this one, the length measure of probability, to reach this thing, when I am teaching to master degree students, it requires 1 month. Okay, to develop this idea, we require 1 month time. Whatever I am just saying. So don't, if you are getting stuck little bit, don't worry much. You read in this direction, gradually it will be clear to you. But for your course, it will be more precisely defined, and all these technicalities might not come to your exam, or it should not come to your exam. But you at least know the definition. That is the main part. Okay, so here I am giving you the two definitions first. This is known as the probability space. So script A, omega, script A, and P. So omega is the sample space called, or in general any non-null set or non-empty set. Script A is the sigma algebra generated from the subsets of omega, and P is the probability defined on the sets of script. An event, be careful to this definition, that if for a given probability space, if A is a subset of omega and A belongs to script A, then only A is called an event. Many of the book often don't write this part, that A belongs to script A. They just write a subset of omega is an event. That is not an event. Always that is not an event. A must be a subset of omega and A must belong to the script A, then only it is an event. So let me give you an example. It will be clear and it will be also linked to this one. So say for example, you know this thing that omega is 0 to 1. Let us call A is say 0, A is a set, maybe this one, say 0 to 0.3. A complement is 0.3 to 0.3 open to 1 closed, and null set is the null set. So script A, let us assume null set omega A complement. This is a sigma algebra, no problem. Now probability of A is defined as say 0.45. Okay. Probability of omega is 1. Probability of null set is 0. Probability of A complement is 1 minus 0.45, whatever, 0.55. Now, if I ask, given all these things are known, sigma whole set known, sigma algebra known, so you know everything about omega, script A, and P. Now consider a set B, say 0. Like this, 0 to 0.4, maybe this.
Sir?
Yes?
Sir, probability of A should be 0.3.
No. This is here, this is how we have defined by the length. That doesn't mean I need to define the probability or probability assigned to that set. It will be always 0. 0.3 here. This is the definition as given. So probability is a function which is mapping from script A to this. So I can define any function satisfying all those things. This is a function which satisfies all those things.
Okay, sir.
Now if I consider B, which is definitely a subset of omega. But if I ask probability of B, can you tell me?
Not defined.
Not it. Because B doesn't belong to script and B is not an event. So although B is a subset of this, but B doesn't belong to script A, probability of B is not defined and B is not an event. So remember this thing, that a set which is a subset of omega and it belongs to the sigma field defined in that probability space, then only it is an event and then only you can calculate its probability. So eventually probability calculation, let me tell you the true story, that we don't get the probability of all the subsets. It is too huge to handle. We have a collection, just a collection, for which we know the probabilities, like this, in a chart. Set A1, A2, A3, A, something like that. And for them, we know the individual probabilities. After that, what are the sets for which we can know the probability? Then we can have a sigma algebra generated from that sets. That means you do all those union, intersection, countable union, countable intersection, and then finally you end up with the sigma algebra, and for that sigma algebra you will know only the probabilities, otherwise you will not know the probability. So this is how it works, and for the time being you need not worry much about this, but when you will do the courses kind of advanced probability theory or stochastic process, these are the things will be very much important. I hope the faculties who will be teaching those courses, they will emphasize this part. Otherwise, there will be a gap in the theory. Okay. So this is a very important thing you always remember. Here, this definition, we have defined through length, which it will be similar to counting, but we cannot count. So we have taken the length as a replacement, and that's why we have got this probability. Otherwise, we could have get some other probability. And gradually in this course, you will see that, well, there will be many different distributions such that for the interval 0 to 4, you may get some 0 probability, you may get some non-zero probability, but it is not guaranteed that you will always get. And if it is by this length measure or the volume measure that you have said, then it is known as the uniform probability. So uniformly distributed over the space. Okay. So this is typically known as the uniform probability, which we will take it for granted. But construction of uniform probability is the most difficult thing. Rest of the thing are straightforward consequences. Construction of uniform probability is the most difficult thing, and for that a huge theory is developed, and that is known as the measure theory. We will not go for that. That is, there is an entire culture of probability which is known as the measure theoretic probability, and the construction is really, really challenging, but interesting at the same time. Okay. We will consider this definition of probability for granted to this course. And from here, we will do the rest of the work. You will see. Okay. Now, let us define the conditional probability. The conditional probability means when you have two subsets of omega, which are also events, and if some event has occurred and you are interested to know for the other event. So say for example, if somebody is smoking what is the probability that the person may get affected by cancer. Okay. So given that a person is a smoker, what is the probability that he or she will get affected by cancer? Or the other way, given a person affected by cancer, what is the probability that he or she will be found as a smoker? So this kind of thing. So the definition is coming from this interpretation of set theoretic interpretation, which is very easy. That you have the sample space omega, and okay, so let me see what I have written. Denominator of B. Here B is the set, and here A is the set. So that there is some intersection part. Okay. Now it is saying that what is the probability of occurrence of A given B has already occurred. Okay. And that means if it is eventually saying how much information about A is contained in B. Okay. So that information contained is only in the intersection part. So probability of A intersection B divided by the probability of B. So this is the definition. So this is how the conditional probability is defined, and you can easily see that we need a restriction that probability of B must be greater than 0. Otherwise you cannot write it in the denominator. So conditional probability of an event is given by the definition probability of A intersection B divided by probability of B. Now if the A is such an event which doesn't depend on B, that means the conditional probability of B, A given B, is same as the probability of A. Say for example what should I say, that say for example that you will that you will score more than 50 out of 100, and B, you will get dosa in breakfast or chapati in breakfast. So all this thing, whatever is the usual menu in your mess. So given that today dosa has happened and you will score more than 50% in your exam, I hope the way the questions are set, whatever dosa is made in the breakfast or chapati is made in the breakfast, it doesn't matter to you. You will score more than 50% in your exam. So in that case, if it so happens that probability of A is same as probability of A given B, then if you write this thing here, that probability of A intersection B divided by probability of B, and that is same as probability of A, that implies probability of A into probability of B equals to probability of A intersection B. So if this thing holds, then we call A and B are independent if under omega script A. So this part is important, often neglected in many books, that if the probability law, that means omega script A P, they are fixed, then if this thing holds, probability of A into probability of B equals to probability of A intersection B, then it is known as the independent event. If the law of probability changes, the same two subsets or same two events may be no longer independent. Okay, so that is a very crucial thing, that if this thing remains true, then only A and B are independent if this condition holds. Otherwise, they are not independent. So this is the idea of classical, the definition of conditional probability, and as a consequence of the conditional probability, we have the definition of the independent events. Okay. Any query?
Yes, sir. I
Yeah,
have
go
doubt, sir.
Yes.
Sir, if we take case of rolling a dice,
Yes.
sir, if we take two events like probability of coming out to be 1 and probability coming out to 3. What is,
Yes. Then?
sir, sir, these events are dependent, sir.
How?
Sir, P A intersection B comes out to be P A into P B, not, sir.
No, you
Sir,
give the statement properly. You are saying that.
Sir, can I speak Hindi? Can I speak Hindi, sir?
Okay, please.
सर हम केस लेते हैं सर, रोलिंग डाइस का केस लेते हैं सर, है ना?
ओके.
तो उसमें सर दो इवेंट है सर. एक इवेंट है कि प्रोबेबिलिटी ऑफ कमिंग आउट 1.
Probability A is coming out to be 1.
हाँ,
B is coming out to be
डाइस को 3.
What is the event B?
B is the event is coming out of. What is the probability of this rolling device gives 3, sir? Outcome is 3, sir. Outcome is 3, sir.
3.
Only
okay.
3.
Okay. Then?
Sir, here is the sir A intersection B is 0, sir.
A intersection B is the null set.
0. Yes, sir. The answer probability of A intersection B equal to 0, sir.
So if
the probability
of A intersection B is 0.
तो सर सर हम यहाँ पर सर ऐसा लग रहा है ना सर P A into P B not equal to P A intersection B.
हाँ,
P
but
A into
see, hold on. B, if you say that B has occurred in one
yes,
roll,
sir.
In one roll you will get only one outcome, right?
Oh, okay, sir. I get it. Got it, sir. Got it, sir. Got it. Thank you, sir. Okay, sir.
Okay.
Okay. Got it, sir.
Okay. Chalo. ठीक है. Okay. Okay. So here are few technical aspects. Okay. Let me just touch this thing a little bit. Okay. So there are two concepts related to independence. One is pairwise independent, another is mutually independent. Pairwise independent means you choose pair of subsets from script A. And if this thing holds, P of AI intersection AJ equals to AI and into AJ for all I not equals to J, pairwise, only two. Then we say they are pairwise independent. But if you take any collection, any finite collection or countable collection of subsets from script A, like intersection of AI1, AI2, something like that, and if the product law holds as it is defined, that the intersection of all these sets is same as the product of the individual probabilities, then they are called mutually independent. Okay. Now, interesting question is this. Give an example that the events are pairwise independent but not mutually. So I am leaving this thing as your homework. It is a very simple example, but you try it. Pairwise, you will be seeing that they are independent but not mutually. Okay, if you take all maybe more than 2 together, the independence will violate. Okay. So this thing I am leaving as your exercise. Few terminologies are important because you will see in many books and you will see in exams also. That mutually exclusive events. Mutually exclusive events means that AI and AJ, they are disjoint. Disjoint events are known as the mutually exclusive events. That means AI is also an event. When I am saying event, that is a subset of omega and that belongs to the script sigma field. So mutually exclusive events mean disjoint events. And it has nothing to do with probability. It is a set theoretic concept. Mutually exhaustive events, that means their union is the whole set. Mutually exclusive events means they are disjoint events. Mutually exhaustive event means they are constructing the whole set. That means their union is the whole set. That doesn't require AIs need to be disjoint. They might have overlap, but their union is the whole set. And these two ideas, mutually exclusive event, mutually exhaustive event, doesn't depend on the definition of probability. The P function doesn't hamper these two definitions. It must be a subset of omega, it must belong to sigma field, but it doesn't depend on P. Okay. But independence depends on P. Whatever way the P is defined, based on that, whether two events AI AJ or AI AJ AK, whatever the other events will be independent or dependent, that depends on the probability definition. But mutually exclusive event, mutually exhaustive event doesn't depend on the probability definition. It just depends on the set theoretic notion of whatever the omega and whatever the sigma field is. Okay. I hope it is pretty simple idea. Okay. And a partition is known as with the set which is mutually exclusive and mutually exhaustive. That means all sets are disjoint and their union is the whole set. So that is known as the partition. Okay. Here we have few results. I think all of you are familiar with this kind of results. I am not going to prove all of them, but some ideas we can extract out from there. So probability of A complement is 1 minus probability of A. And from that result, we can immediately get probability of the null set is 0. And if A is a subset of B, then probability of A is less than equals to probability of B. Already you have got that example, right? This one. Here. So if you consider well, omega A P and omega is 0 to 1 and probability law is defined as the length of the interval so, and in that sense the length of the interval all are same, A to B So, so probability of A to B is same as probability of A open, B closed, A closed, B open. Probability of A open, B closed, and probability of A closed, B closed. So they are same for any of the interval, and you can easily see that AB is a subset of either of this and this and this and this. So AB is a subset of, I can say, this, but probability of AB is same as probability of AB. So we can write this is less than equals to. So whether the set is larger set or smaller set, it matters, but the equality sign can be there. You have already got that. So probability is defined on the intervals, and the probability is the length of the interval associated to it. Now, by De Morgan's law, you can get the fourth one, that probability of one intersection of AI complement is same as 1 minus probability of union over AI. Okay. Now, let us go by the fifth one. Fifth one is also trivial because probability of A union B, you can get it from the Venn diagram. I think you are familiar with it. So if this is omega, A and B. So first you measure the probability of A, which is this. Then you measure the probability of B. Then you subtract the double counting area. A intersection. Now, what I am asking is to extend this idea. Okay. So probability of A union B union C. How can you extend this thing? A, B, C. What will be the outcome for this one?
P of A
Sigma P of A.
Probability of A plus probability of B plus probability of C. Then
minus
first
P
you
of
take the individual, then
Minus P intersection
B of A intersection B.
A intersection B minus probability of B intersection C minus probability of C intersection A. Then
plus probability of A intersection B intersection C.
Probability of A intersection B intersection C. Okay. Now if I ask you to make it for A, B, C, D, 4 sets. Okay. So in general, if I ask for this, I equals to 1 to n AI. What will
So
it be?
there is a pattern, no, sir. There is a
Yes,
pattern,
of
sir.
course.
Summation of.
Equation expression.
Okay.
So plus minus plus minus.
Plus minus and how many sets you are choosing. Okay.
Yes, sir.
So this is the collection
Yes, sir.
of
It's De Morgan.
one set. Right.
Yes.
Here 2 sets.
Yes.
Here 3 sets.
Yes, sir.
Right. So how many ways you can choose one set?
N.
N. Okay. So probability of one sets. Okay. Then minus probability of two sets plus probability of three sets. And in general, how can you write? Last element will be probability of n sets. And all are in terms of intersection. That is, so in general, probability of, say, if I write k sets, what will be the sign?
So it depends, it's even or
minus 1.
Power?
K minus 1.
K minus.
K minus.
So minus 1 to the power n.
K minus 1. K minus 1, sir.
So this is the way. Now, how many elements in one set?
Sir, NC1.
NC1 elements. So this term will contain n choose 1 elements. How many elements here?
NC2.
N choose 2 elements. How many times here? N choose 3 elements.
And
in general, n choose k elements. And lastly, n choose n, that is 1 elements. So this is the thing, if you remember, many of the problem will be solved. Okay, so now let me ask you one question. This one, let us see. So here, this is the expression. Minus 1 to the power k minus 1 sk, where sk is all possible choosing that thing that is written under this summation and sk, and this summation will contain this n choose k many terms. Okay, this sk summation will contain n choose 2 many terms. Now let me ask you this question. Suppose n letters are put in n envelope distinct by address, and letters are distinct, envelopes are distinct. What is the probability that no letter will reach to the correct address? Well, sigma algebra done, independence done, union intersection done, this thing. Sure, we are within time. So now tell me how you can implement this idea to address this problem. Is the problem clear?
Yes, sir.
yes, sir.
It happens in your exam time. People comes with mobile phone, and suppose everybody is given a blank envelope, then also students are in a hurry. They put the mobile in the envelope but forget to write the name on the envelope. So many white envelopes are there and no name there. And when they are going back after the exam, they are also in a hurry. They pick up one of the envelope thinking that it is his or her and return. What is the probability? Nobody will get back his or her own mobile. Same problem.
So it's the probability 1 by e.
Okay, so step by step. Step by step.
1 minus.
How will you write it? Writing probability is a very, interesting thing and challenging thing, because some problem you might be able to do easily, but if you are not able to write it properly, the higher level problems will be difficult to handle. So n letters, so I am removing this one. N letters to go to n envelope. Okay. So if I define AI is the ith letter is put or is kept in the correct envelope. Then probability of no match, that means no letter is going to the correct envelope. This is known as, how can you write this event in terms of AIs?
Total probability minus union.
AI complement.
So first this thing, probability of intersection of AI complement, I running from 1 to n. Is it okay? Nowhere it is correct. And that thing by De Morgan's law, you can write probability of union over I running from 1 to n AI. Now it is pretty simple because this is 1 and you know the formula for this part. Okay. So let us write it down as it is given. I am writing it down here. So sum over I running from 1 to n minus 1 whole to the power k minus 1 is k. Okay. So I running from 1 to n minus 1 whole to the power k minus 1. This part is okay. Now what will be the value of sk? What exactly sk means in this situation?
K letters in correct place.
K letters in correct place. Okay. And how many elements will be there in sk? You already know. This is S1, right? This is S1. This is S2. This is S3. This is Sk. How many terms will be there according to this summation? This summation. How many?
N choose K.
N choose K. And each of them will have the equal probability. Okay, so in general we can consider, maybe say without loss of generality, first k terms let us fix such that they are getting the correct envelope, that is ensured. So n choose k many such elements will be there with equal probability, and what will be that probability that in this position correct, here don't know. Only this is ensured that this position n minus, so here you put the correct thing, here n minus k elements, so n minus k factorial divided by total number of n elements, so n factorial. You do little bit cancellation and you will get 1 minus, again I running from 1 to n minus 1 whole to the power k minus 1, and you will get 1 by k factorial. And if you make the bracket open here, you will get 1 minus 1 plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial and so on. So it will be plus minus 1
Power k
to the power n 1 by n factorial. Remember there is a minus sign, so it is coming as n. Okay. So this is the result, and what will be the limit?
1 by e.
So limit n goes to infinity, probability of no match is e to the power minus. So this is an interesting finding. And lastly, let us talk about the Bayes theorem.
Sir,
Yes.
sir,
Yes.
in that n minus k factorial by n factorial.
Uh-huh.
So like, but I think those remaining n minus k, there may be a chance of getting into right place, no sir.
Yes, that. But we are not interested for that. We have just mentioned that the correct allocation is only in these k places. Whatever is happening there, we don't bother. So whether this, so in n choose k, I have n choose k elements will come with equal probability, and for each of them I have prefixed these prefixed k values. Instead of first k, you can also do the same thing for the last k, or any specified number I1, I2, Ik, doesn't matter. You are just interested that only in these locations correct placement of the letter is happening or not. Whether the others are getting correct or not, that is not the interest here. Only in those locations it is getting correct fill up or not, that is the probability. Is it okay?
So, but sk means definitely only k must be in the correct places, no sir.
Say again?
So like sk must means like only k places must have the correct places, like in the correct position, no sir.
Look, I am saying A1 intersects A1 intersection A1 intersection A2 intersection AK. I am not saying AK plus 1 complement, AK plus 2 complement, AK plus 3 complement. That is not I am saying. If I write with this that AK plus 1 complement, AK plus 2 complement, AN complement, if you combine this, I mean intersection, this with this intersection, then it means only this k will get the correct and this will not get the correct. Do you got my point?
Okay, sir, got it. Thank you.
Got it. Okay, lastly, Bayes theorem. But people are very much enthusiastic about Bayes theorem, but I don't know why I don't feel much interest about it, because it is a very natural consequence of studying or human nature, that if you have information you will use it. Okay, so but anyway, let us see. So what it is saying that if A1, A2, AK are partition. So you remember what is partition? They are mutually exclusive and mutually exhaustive. That means their union is the whole set, their intersection is the null set. Any two if you choose, their intersection is the null set. A partition of omega, and omega AP is the probability space. Probability is well defined. Probability of AI individually, they are positive, and probability of B is also positive. Then for some B, which is a subset of omega, and definitely it must be an event of subset or element in script A, then the conditional probability of AI given B can be expressed in this form: probability of B given AI into probability of AI divided by somewhere I running from 1 to k probability of AI, B given AI into probability of. So let us just prove it because it is formally needed. So just to visualize, try to visualize this thing first. That this is your omega and it has partition. in many different ways. Okay, so maybe this is your A1, A2, A3, A4, A5, A6, and so on. And B is a set, something like this. So this is B. So what we are interested about? We are interested about probability of AI given B. Okay. Probability of AI given. So probability of AI given B, that you can write immediately, probability of AI intersection B divided by probability of B. Now, let us work on the denominator first. That probability of AI intersection B divided by, I can write probability of B intersection omega. Any problem? B intersection omega is B. Okay. Now, omega, you can write union over AI, I running from 1 to n. Okay. Or 1 to n, 1 to k, doesn't matter, whatever is the number, what I have written here. K. Okay, so let us write k. So 1 to k. So I will replace this omega by union over AI. So here, probability of AI intersection B, let me use other index, probability of B intersection AJ, union over J 1 to K AJ. B probability of B intersection union over AJ, J running from 1 to K. Okay. Now you distributive property of intersection over union. So this is probability of AI intersection B divided by probability of union over J running from 1 to K AI or AJ intersection. Now notice one thing, as AIs are disjoint, AJ intersection B, they are also disjoint. This part is disjoint with this part is disjoint with this part is disjoint with this. Okay. So you can immediately split it, AI intersection B divided by sum over, from the third property of axiomatic definition, J running from 1 to K, probability of AJ intersection. Now the rest part is trivial, just use the definition of conditional probability, multiply and divide each term. I am doing here, probability of AI divided by probability of AI and probability of AJ divided by probability of AJ. Okay, so if you combine this one with this one, but you will get probability of B given AI into probability of AI whole divided by sum over B given AJ, probability of AJ, J running from 1 to K. That's it. Okay, so now we have 15 minutes time, so let us try to see a quick example and then we will see something interesting. So suppose in a city, 40% male population and 60% female population. Among male smoker 50%, female smoker 30%. Probability, let us ask for this probability that a randomly chosen smoker is a male. Randomly chosen smoker is a male candidate. How will you compute this thing? So you are asking for male when it is given it is a smoker. Okay. So probability of male intersection smoker divided by probability of smoker. So probability of smoker given male into probability of male divided by probability of smoker. And probability of smoker you can split into this way, that probability of smoker given male and probability of male, and probability of smoker you can split according to this formula, probability of smoker given male into probability of male plus probability of smoker given female into probability of female. So this probability, what you are seeing in the denominator, it is often known as the compound probability. This expression is often known as the compound probability. So please tell me what will be the final answer. So probability of male is 0.4, probability of female is 0.6, probability of smoker given male is 0.5, probability of smoker given female is 0.3. Now you please tell me the answer. Let's say is
10 by 19.
10 by 9. Okay, correct. So this is the thing. Professor Somesh Kumar will share you, or maybe through us, many more assignments, but you need not, submit them for your exercise. So whatever the necessary thing we have done for this introductory probability definition and laws. Now let us see some interesting examples where you can use. I am leaving this one also, this interesting question for your homework, that a quadratic equation u square minus root over y u plus x equals to 0, where x and y is a randomly chosen point from uniform unit square. What is the probability that the quadratic equation has real root? So you try. But here we are going to see some example which will enrich our idea. So give a randomized algorithm to approximate the value of pi. And similar question, give a randomized algorithm which will approximate the value of e. Both are non-terminating, non-recurrent decimal, transcendental number. So we can just approximate them. You know, maybe in your computer science course you have already done the approximation of e. Your function you have written, recursive relation you have done, and from there you have approximated the value of e. But through statistics also you can do it. So any logic or algorithm to develop or to approximate the value of pi, how can you do that?
We can choose a number which lies between the squares of x equal to -1 to 1 and y equal to -1 to 1, and then we will see if it lies within the unit circle. So that
Okay.
probability will
-1 to 1 and -1 to 1. Okay. Um, do you really require -1 to 1? Can you do it within unit square 0, 1 cross 0, 1?
yes, sir. For that we will just shift the center of the circle to half comma half,
No,
and
say
it
for
is it.
example, within
Yeah, that
this
will.
unit square, you can have how much area?
This will also be pi by 4.
This will be pi by 4. So what you can do, you can choose a random number as you were saying between 0 and 1, and you can choose two random numbers, one for x, another for y. And if the xy point lies here, you will count 1. If it lies here, you will count 0. And in this way, you will be doing this thing repeatedly, maybe 10,000 times or 1 lakh times, and you will be keep on doing this work, and you will be interested to see where it is going. And whatever it is supposed to convert, it is supposed to convert to pi by 4, and you multiply that number by 4, you will get the value of pi. Okay. So anybody has any query? But what will be the mathematical condition to check whether this point is lying within the circle or outside the circle?
The sum of squares should be less equal to 1.
So distance should be less than 1.
X square plus y square should be less than equals to 1. That is the condition. So let us see the graph. I have the code is written, but code is not written in a very efficient way, but written in such a way that it is easily understandable for fast reading. Okay. So A1 is 0, B1 is 1, A2 is 0, B2 is 1. So uniformly data are generated from A1, B1 and A2, B2, so 0, 1 cross 0, 1. Then it is checked whether it is lying between, satisfying this condition within the circle, and then how much within the circle proportion multiplied by 4. So yeah, gradually you can see first initially it will have some fluctuation, but gradually it will be converging to the value. And if you see the plot, this is how it looks. So the red dots are falling within the circle and the black dots are outside the circle, and the in green boundary is the boundary of the circle. Okay. So with this idea, can you please tell me how you will be able to approximate the value of E? This is pretty simple. Which function will you choose? So ultimately you try to understand this thing. This is a very important idea, and all computational statistics is based on just this simple idea. What we have eventually done, pi is a number which is bigger than 1, but pi by 4 lies between 0 and 1. It is we have converted the situation in such a way that we are approximating a probability, and that probability approximation we have converted in another form which is area under the curve. So eventually this red dot region, that is the area under the curve, and that is pi by 4. So this is another way to do integration. Numerical integration, this is another way to do numerical integration. And you can see that gradually the fluctuation is going to 0. and that gives the boom in the computational statistics realm. Whatever we are doing through computer science, by the help of computer science, only because of this result. And this result is technically known as the weak law of large number. We will state and prove the theorem later on. But this is the whole idea. And entire computation of probability and statistics is, the underlying thing is this. So can you tell me the what function? Here we have chosen the function x square plus y square, and we have put the restriction whether it is less than 1 or not. So to compute the value of e, can you please give me the function?
So we can use
e to the power
y
x
equal
minus
to
1.
1 by x.
Yes. Yeah, go ahead.
Y equal to 1 by x from 1 to 2.
Yes, correct. So you can go for 1 to 2. And okay, so let me just try to draw it here once again. So this is one problem, and another. So 1 upon x, one to 2. So this is your x direction. It is 1 at 1, and 2 it is half. So, and this function is 1 upon x. So area under the curve, how much? Integration 1 to 2 1 upon x dx. What it will be?
Natural logarithm of 2.
Log e base 2. And that is the area. Right. So what will be the value of e? If what it will be?
2 power 1 by n.
2 power 1. Okay. So your job is to calculate the area. Now you need to draw x coming from 1 to 2 and y coming from 0 to 1. Okay. So that is the thing. And how you can draw x from 1 to 2? If you know it, draw x from 0 to 1, add 1 to each of the element, you will get the data from 1 to 2. So that is the simple idea. And again, you can see that we can do this work. Okay. So here you can also count in this way that xi yi less than equals to 1 and 2 power 1 upon area. So you cross check the code and you can copy and paste. It is written in R, so you can copy and paste in any maybe Jupyter Notebook or R Studio and online R, whatever. And again, you can see initially there is some fluctuation with the iteration, but if you go for 10,000 iteration, it gradually matches the true value of E. So here again, this is the graph. Sorry. Yeah. So this is the graph where the red dots are within the area, black dots outside of the area, and 2 to the power 1 upon the area is the true value of the E. And with one more interesting question, I am leaving you this class. So suppose two natural numbers are chosen randomly. Find the probability that they will be co-prime. GCD is 1. Okay, this is I am leaving as a fun exercise. You will learn so many things from here.
Sir, can you repeat? What is the
question? Two natural numbers are chosen. I will share you in the written note, but here two natural numbers are chosen, n1, n2, randomly from the set of natural numbers, GCD of n1, n2 equals to 1. Find the probability of that. This is fun exercise. It is not a compulsory exercise. If you find it difficult, you can leave it. But if you are really interested in mathematical details, and not only mathematical details, it has so many connections to the very interesting number theoretic results, you will find really, really interesting. So you try this one. Two natural numbers are chosen randomly and GCDs. So in the next class, we will start random variable, the definition of random variable and what the features we can study of random variable, later on the special cases of it. Okay, thank you.
Thank you, sir.
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 Thank you.
So you'll share the notes, right?
Yes,
Lattice notes.
everything is already uploaded. You can see in your MS Team. If you go by files, oh, it is getting slow. Yeah. Your class materials. Here, I will the first day slide and the first day note I have uploaded, and I will add this one. Also, it will be available here. Okay.
Okay, sir. Thank you.